Good afternoon, everyone. I would like to talk about rift axis parallel lower crustal flow, and I would like to emphasize that this is a big part of collaborations with people from the Royal Holloway University in London, the GFZ in Potsdam, as well as the company LaVision, and of course, people from the University of Bern. So, lower crustal flow, it can occur if we succeed with if we meet certain requirements such as crustal thicknesses which should exceed 20 to 25 kilometers, and the lower crustal temperature should be above 500 degrees. So especially the first point then leads to the fact that lower crustal flow is largely restricted to the continental crust. If you look at the top sketch from Hopper and Buck, you see that indeed this lower crustal flow occurs horizontally, and it flows towards areas of maximum thinning within the upper crust. Now, this feature can be broken down to a very simple mechanism, which is nothing else than differential topography within the upper crust. So where we have a thicker upper crust, we create a pressure gradient, which then induces ductile flow in the lower crust towards areas where the upper crust is thinned. So this happens parallel to the extension direction in a rift, but we can ask ourselves, what about the third dimension? So if you look at this figure from Brune et al. 23, we see that we have different stages of rifting from the early rift initiation all the way to the development of continental passive margins. But we can also look at this sketch and see it as a fixed time frame and see different parts within one continuous rift where we simply have different stages of deformation due to a deformation gradient along the rift axis. And with that in mind, we therefore should also expect lower crustal flow that flows towards areas where the deformation is highest, so parallel to the rift axis. And such settings, they indeed occur also in nature. They're known as rotational rifts. And in a rotational rift, we basically have the rotational opening of the rift due to a divergence velocity gradient along the rift axis. So we have the highest deformation in this area. And as we go towards the rotation pole around which the undeformed blocks rotate, the deformation increases. And during my PhD, I was actually looking at exactly such rotational rifts using analog modeling experiments. And the development, especially in monitoring and also quantifying the deformation in analog models, has massively increased over the last 200 years. Here from the first very simple experiments from Hall to nowadays state-of-the-art monitoring setups where we have digital cameras to monitor top view deformation, from which imagery we then can further use digital image correlation to quantify the deformation. And in Bern, we are in the lucky position to also have access to such a medical X-ray CT scanner, which allows us to X-ray scan our models during the model run, which gives us some further insights into the transient internal deformation, from which we then again can apply digital volume correlation to gain quantitative insights into the internal deformation. And we've done that using a relatively simple two-layer crustal scale model setup. Here you see we have this brittle sand layer to simulate the upper brittle crust, which sits on top of a viscous layer to simulate the lower crust, which should deform in a more ductile manner. And the machine that we use for that allows exactly for these rotational motions. You see it here. We have at this point in the model, we have a rotation axis. So everything to the right side opens up, causing our rotational rifts. whereas on the other side of the model, we then create contraction, but I don't want to go too much into detail regarding this part of the models. And simply by opening these rotational rifts, we would then expect a lower crustal flow, which is parallel to the rift axis, which flows away from the rotation axis. We played with different model setups. We also used additional gravitational loadings above the contractional domain to actually enhance this viscous flow and study it. But if you first look at a very quantitative description of the model deformation, we have on the left side a model which is a reference model where we have an initially flat topography, so no additional load on the compressional domain. And on the right side, we have a model where we have an additional gravitational load here in this model domain. And we can see, or we can say that the deformation at the finite state, at the final stage of the model run, is in both cases fairly similar. So we have these rift boundary faults as they propagate towards the rotation axis, and as deformation increases, we create this rift inward migration of the deformation, creating these intra-rift faults, which are faults then of second and sometimes even third generation. But if we have a look in a more quantitative manner, it will all look a bit different. So what you see here are strain maps. We show the incremental strain rate here, meaning that we have increments of 1 minute for each time step. And you see again on the left side, we have the flat topography model. On the right side, we have the model with additional gravitational loading. And we have different time steps where we see different stages of extension. So in the reference model, as expected, we also see that we have activity along the rift boundary faults and they propagate towards the rotation axis. And as deformation continues, we see that we then get this rift inward migration. We have the activity of intra-rift faults, and this coincides with the ceasing along the rift boundary faults. So here we see that while the intra-rift faults become active, the rift boundary faults lose their activity. And this goes so far that in the end, we even have a third generation fault, which is an intra-rift fault right on top of the rift axis. And then we have this stepwise broadening towards the rotation axis where the rift boundary faults are still active. If we compare that and look at the gravitational loading, here now it looks a bit different compared to the quantitative view. We see that the rift propagation, first of all, seems to be delayed. So at the same stage, the rift in its length is laterally not fully developed. And that also influences, of course, the timing of the onset of the intra-rift fault activation. So, but we are interested in the lower crustal flow and especially the rift axis parallel lower crustal flow. And therefore, we will now have a look at the cross section, which is indicated here by this dashed line. And what you see here are basically 4 model runs where we subsequently increase the gravitational loading here. And it's no surprise that the magnitude of this rift axis parallel flow increases with the increasing gravitational loading. But I would like you to focus on this top figure that you see here, where we not just only have no additional gravitational loading, but on top of that, we also have no contractional domain in this model. And even in that case, so if you have a purely extensional model, we create this rift axis parallel flow that moves material away from the rotation axis towards the point of highest deformation. And that seems not surprising in this case, especially because we're in a rotational setting where we expect to have this flow due to this deformation gradient.
Yeah, that's 10 minutes, Timothy.
Thank you. So what about orthogonal rifting. We also looked at this case, and for that we revisited a model from Swan et al. 2018 study. We applied the same conditions where a lower crustal flow should occur. And what I looked at in this study is that rift propagation and segment interaction. Because in a orthogonal rift, they don't develop simply out of one continuous fault that's immediately there, but rather out of individual segments that propagate and eventually start to link and interact. And if they interact, if they have a stepping, in this case a right stepping, and they start to interact, they confine such a rift path structure in the middle, in the center, which eventually rotates about a vertical rotation axis. So again, we applied here digital volume correlation to get quantitative insights. Here you see we were able to quantify this deformation of the block, which gives about a mean rotation of about 4 degrees over the entire model run, which is quite consistent with also the findings from Swan et al. 2018. But this is just for the brittle domain. So if we look at the lower crust, at the viscous domain, we see something interesting. If we compare that, especially if we compare the extension parallel displacement direction with what we see in the upper crust, we see that in the lower crust we have domains below the rift path structure which show an opposing flow direction compared to how the material is stretching at the surface. And if you look at the second horizontal direction, which in this case would indicate motion in this direction and in this direction, we see again that below the rift path structure, we create these two peaks in the flow where material is flowing out of the model domain and it flows parallel to the rift axis. We can now both of these rift segments consider as small individual rift segments that seem fairly similar to these rotational experiments I showed you before. And therefore, it makes sense that we have this deformation gradient from the area where they propagate from towards the tip of the rift segment. And in that sense, we should also expect in such an orthogonal rift to create a flow that flows opposingly to the rift propagation. Now, the problem in nature with detecting such rift axis parallel flow is that we only can see that if the rift axis parallel flow starts to create a stretching fabric. And for this, we were looking at the finite strain in our models. And again, here you see the upper crustal domain, and you see that the stretching axis of our strain ellipse is parallel to the stretching direction of the overall model domain, namely the rifting direction, and that's as it should be. However, if you look in the viscous domain, we see that the stretching axis rotates by 90 degrees. And that's exactly what we also see in the flow. But now, using these strain ellipses, we know for sure that this rift axis parallel flow is strong enough to create such a stretching fabric, which is perpendicular to the extension direction at the surface. So this has some implication for nature and also some take-home messages, or to summarize what we've seen before. And what we saw is that this rift axis parallel flow is driven by this lateral deformation gradient, and it may delay the rift propagation, as we have seen in the top views. This ductile flow is quite pronounced in rotational settings where we have a pronounced deformation gradient along the rift axis, but our models show that it's also likely to occur in rift settings without such a divergent velocity gradient. And if this flow is strong enough, then we can create such a stretching fabric which is perpendicular to the extension direction that we see at the surface. And that implies that in nature, if we have lower crustal material that over time emerges and comes to the surface, we have an old rift axis parallel fabric that eventually gets overprinted when it comes to the surface by the stretching fabric due to the extension. And for this, there are natural examples which support this case, and our models also support ideas that people develop due to these observations in nature. So with that, I'm finished and I'm open for questions. Thank you very much.
Thanks very much, Timothy. Do I open the floor for questions? Okay, I've got a question in the meantime. I mean, you mentioned about the difficulty of detecting the lower crustal flow in nature. Is it possible to just do a simple, I don't know, calculation of the observed versus predicted crustal thickness in rifts to try to detect this process, like in the magma poor rift, for example? Would that be something to weigh, or?
It's something I didn't look into further, but my hope was that the insights from these modeling studies eventually would maybe help to predict what's going on in the lower crust, especially at places where the lower crust is not exposed. So, for example, if you have a rift pass block and we can measure its rotation, and we can measure the deformation in the upper crust, can we get from that to some insights about what's going on in the lower crust? And I haven't looked further into that, but that would be eventually a goal of this study, yes.
So also, what are the kind of rates of flow, like if you extrapolated from your models to nature?
To be honest, I didn't write it down here. It's been a while. I would need to look into the papers where we actually did the scaling back to natural flow velocities. It's a bit embarrassing because I don't have them in mind right now, but they should be in one of the papers which are published.